Okay, so I will focus on gamma ray bursts, and I will try to show how FCRT observations have been fundamental to progress our understanding of these sources. So I have a few slides to introduce the physics and the observations from these sources. So there will be some overlap with what Paolo already said, but I think it's good because most of you are not working on gamma ray bursts, so it's okay to repeat some basics information. So the emission that we receive from gamma ray bursts can be divided into separated phases called prompt and afterglow emission. The prompt emission is the gamma ray burst itself. So we receive flashes of soft gamma ray radiation, hard X-ray, that last in total few tenths of seconds for long gamma ray bursts or less than 2 seconds for short gamma ray bursts. And the spectra are non-thermal. No? Let's try like this. No?
No, sono ancora così. Okay, no, prova a uscire, vediamo di capire. Forse dovresti, secondo me devi condividere tutto lo schermo e non solo la finestra. Prova un po'. Hai fatto entrare, riproviamo? Sì, giusto. Prova ad andare su tutto, gira. Cioè, non va. Ci stanno pure registrando. Allora, come mai? Ah, prova slideshow. No, slideshow va avanti da solo, però poi.
Posso mettere in pausa?
Bella cosa. Gira. Ok, pausa. Adesso prova a girare con le freccette. Ah no, certo. Niente, ma che cosa assurda. Ha uno schermo solo. Esatto, stop alla condivisione. Stop sharing. Ah, show my screen anyway. Eccolo lì. Questo qui, prova adesso. Adesso prova di nuovo. Col full screen. Cambia slide.
Sì.
Ok. Cambia slide. Manco per il niente. Esci dalla condivisione e rientra, è l'unica cosa che mi viene in mente. Allora, aspetta, stai ancora condividendo, fai cancel.
Paolo, stai condividendo?
Ah, ecco perché. Sono io che sto danneggiando, ti riproviamo? Sì, hai ragione Tullio. Strano, però solitamente si dovrebbe... Perché you can override someone. No. Non riuscì. Me l'hai mandata perché la fai a me?
Sì.
Sì, claro. Ok, I have a copy of Lara's presentation and we are going to switch, sorry. Carico subito. So, you can hear me? Yes, the settings should be again the same. And now if I share entire screen, share, and this view, enter full screen. Can you see the slides running from a remote?
Yes.
Okay, so and you can hear.
Okay.
Okay,
thanks,
sorry for
Paolo.
the delay.
Sorry. Okay, so I was going to introduce the two different phases of the emission of gamma ray burst. Prompt, lasting typically 20 seconds for long gamma ray burst and less than 2 for short gamma ray burst. And the light curve is very regular. As you can see, we have pulses, very short pulses of soft gamma ray radiation. And at some point, this emission stops and is followed by the so-called afterglow radiation, which is very different. Here, the flux decays in time as a power law in first approximation. And we detect this emission basically over the entire electromagnetic spectrum, from radio to TV energies. And this emission is detected up to days or weeks, depending on the frequency at which you are observing, but even months in the most extreme cases. So this is the basic model that is involved in order to explain all these observations. So Paolo already discussed the progenitors of gamma ray burst. So let's start from the when the jet has been already launched. So we have a relativistic jet that is moving in this direction, and we don't know exactly the composition of this jet. What you see here is a possible explanation if the jet is matter dominated. So the energy is stored in kinetic energy of the particles. Let's imagine that the jet is not uniform, but can be described by well-separated shells. And if these shells collide, because they don't have exactly the same velocity, so at some point they can collide, in this collision, some internal energy is released and is used to accelerate particles. And the accelerated electrons are expected to radiate synchrotron photons, because you have energetic electrons in a strong magnetic field. So synchrotron emission is expected to be the dominant radiative process. And this model is used to explain these flashes of gamma ray radiation that we detect. There are many open questions. As we will see, the spectrum we receive is not completely consistent with synchrotron radiation. So this means that we still don't know exactly what is the radiative process producing the gamma ray emission that we observe during the prompt. And this makes also difficult to study the properties of the emitting region, magnetic field, bulk Lorentz factor, the distance of the region where the prompt is produced, the distance from the central engine. It should be something around 10 to the 13, 10 to the 15 centimeters, based on theoretical considerations. And we don't know the dissipation mechanism. Here we saw internal shocks, but actually if the jet is Poynting flux dominated, then we should convert magnetic energy into energy that is used to accelerate particles. So, for example, with magnetic reconnection events. So, as you see, there are a lot of open questions related to the production of prompt emission in gamma ray burst that reflects also on our knowledge of the jet itself. At larger distances, instead, we expect that the external medium where the jet is expanding is starting to affect the jet itself. It will decelerate the jet. So you can think of this interaction again as a collision with the external medium this time. And in this collision, again, some internal energy is dissipated, and a fraction of it is used to accelerate the electrons. So again, you have accelerated electrons in a strong magnetic field. You expect synchrotron radiation. And this is the model invoked to explain all the afterglow emission, and it works pretty well. Okay, so in this second phase of the gamma ray burst radiation is better understood. So how do we catch a gamma ray burst? We need a wide field instrument sensitive in the soft gamma ray energy range. Okay, so here I listed the main instruments and satellites that allow the study of gamma ray bursts. The first one was MAXI on board the Compton Gamma Ray Observatory that was sensitive in this energy range here, 20 keV to MeV, so perfect to detect the prompt emission from gamma ray bursts. Now we have Fermi, so the GBM is sensitive in a similar energy window, a bit larger, and has detected prompt emission from more than 4,000 gamma ray bursts. In fact, some of them, a small fraction, is detected also by the instrument sensitive to higher energies, the LAT. And then, of course, we have Swift that is catching gamma ray bursts thanks to BAT, but is sensitive in a narrow energy range, 1550 keV. Okay, these are some examples of light curves during the prompt emission. So what I want to show here is that we don't have a typical light curve for gamma ray bursts. All gamma ray bursts are different one from the other, so you can have single pulses or two or more well-separated pulses. You can have pulses that overlap to each other, very narrow spikes, quiescent time, so a period of time where apparently there is no emission. So we have a very different morphology in the light curve. These instead are examples of light curves during the afterglow emission at different frequencies. Radio light curve, so here each color is a different gamma ray burst. We see here optical observations. So as you see in first approximation, the flux decays in time as a power law. In this plot, you can see afterglow emission in the GeV band detected by LAT. Also here, the flux decays in time as a power law. And finally, you have soft X-ray observation. So here, actually, the first part is prompt emission from BAT. You can see here the pulses, even though in logarithmic scale, it's more difficult to appreciate. And then this part instead is the afterglow. And so as Paolo already mentioned, a Swift with XRT in particular allowed to discover the early afterglow that was not accessible before Swift. And here are the main results for gamma ray bursts of the Swift mission. So XRT discovered that the light curves in the early part of the afterglow emission are very different from what we expected. So this is the afterglow that we were observing also before Swift, but then Swift allowed to study this region here between the end of the prompt and the beginning of the afterglow. So this is a shape that has become quite canonical because most gamma ray bursts present this steep, flat, steep shape. Paolo already discussed the plateau. The origin is still very uncertain. And then XRT also discovered that there are X-ray flares, very common. These are probably related to the final phases of the prompt emission when the emission becomes softer. However, there are flares also at quite late times that are more difficult to explain. So also here, the situation is not completely clear. So many open questions. And then there are also light curves that instead behave exactly as expected, as single power law, as the model predicts. Okay. So I'm sure that if I asked you what was the main progresses in the field of gamma ray burst concerning discoveries by XRT, you would answer pointing to this slide. So XRT made possible the study of early afterglow. We discovered this strange feature in the early afterglow, this canonical behavior that was unexpected, X-ray flares, and this is certainly true, but I'm not going to discuss these results in this talk because I want actually to focus on prompt emission. So I'm sure that most of you heard that Swift, and BAT in particular, were not the most suitable instrument for the study of prompt emission. Why? Because I mentioned it also before, the energy range of sensitivity of BAT is very narrow. So it was not meant to bring us some progresses in the study of the prompt emission. But what I want to show here is that BAT, together with XRT, unexpectedly allowed us to make an important discovery, the most important, in my opinion, progress in the study of prompt emission over the last years, okay? So let's focus on prompt emission. This is a typical spectrum of prompt emission of, from a gamma ray burst. So you see it's described by two power laws, smoothly connected. So it's a non-thermal spectrum. So we need to invoke some non-thermal process. And so the shape is consistent with what we expect from synchrotron radiation from non-thermal electrons, okay? But let's make a more detailed comparison. So from synchrotron radiation, what are the expectations? So sub-theory. Let's assume that we have a non-thermal power law of a non-thermal population of electrons accelerated by some unknown mechanism, okay? So as I discussed before, we still don't know the details of particle acceleration in prompt emission, but we believe that there is a non-thermal process working during this phase. So the usual assumption is that at the end of this particle acceleration process, the spectrum of the electrons is described by this power law from some minimum Lorentz factor to some maximum Lorentz factor. And P is the spectral index. So this is the electron distribution at the injection. So after the end of the acceleration process. The acceleration process keeps injecting electrons with this shape, but the electrons in the meantime start to cool, to lose energy because they radiate synchrotron emission. So of course, by cooling down, the Lorentz factor decreases. And this is the equation that gives you the Lorentz factor of particles losing all their energy after some time t. Of course, it depends from the magnetic field. Strong magnetic field, electrons cool down very quickly. In the case of prompt emission of gamma ray bursts, we probably are in this situation here. We have strong magnetic field, gamma C, gamma cooling is very small. So we start to populate also this part below gamma M because we take high energy electrons that lose their energy and go here. So at the end, the final distribution is this one. So this describes the energy distribution of a cooled population of electrons. From the theory, we know that this electron distribution here should radiate a photon spectrum, synchrotron spectrum that has this shape here. So two peculiar breaks, one referring to the minimum injection energy of the electrons, and the other one at much lower frequencies, which reflects the cooling frequency of the electrons. Okay, and these are the predicted spectral indices. So now here we have the theory and here we have the observation. Let's try to compare them. Of course, since we see two power laws smoothly connected here at the peak energy, it means that we are looking at this part of the synchrotron spectrum. So we can identify μm, the frequency of the electrons with the minimum injection Lorentz factor. We identify this break here with the peak energy of gamma ray bursts, of the spectrum of gamma ray bursts. But then there is an immediate consequence here, that this slope here should be minus 1.5. When I give numbers, I refer to the photon spectrum, okay? So there is always some confusion here, but you have to add 2 in order to infer the actual slope in this representation here. So this will be plus 0.5. But let's always work with the photon indices, okay? So the expectation is minus 1.5. What you see here is a distribution from many gamma ray bursts of the measured photon index of the prompt spectrum. So here many gamma ray bursts have been fitted, and what we are representing is a distribution of the photon index in this part of the spectrum. As you see, it peaks at around -1, -1.1, while the expectation from synchrotron radiation is -1.5. If you put together many spectra and convolve, you can always obtain something softer. So in this side here, never harder, okay? So this is a problem to explain the -1. You can explain with synchrotron only this small tail of gamma ray burst. All the rest are inconsistent with synchrotron theory. Can XRT help to solve this big issue with the interpretation of the radiative mechanism in gamma ray bursts? Well, the answer is yes, because XRT sometimes, unfortunately, in a small fraction of cases, observe the gamma ray bursts during the prompt emission. So it's not just observing the afterglow, but was quick enough to observe already the prompt emission. This can happen in 2 cases. Either the gamma ray burst has a prompt emission that lasts for a lot of time, so a few hundred seconds. Some extreme cases, but can happen. And then XRT has the time to point to the source. Or, like in this case here, there is a precursor that triggered BAT, then a quiescent time. In the meantime, XRT is pointing to gamma ray burst. And so when the main part of the prompt emission begins, XRT is already looking at the source. Okay, so here we have prompt emission observations in a wide range of frequency. This is a spectrum, so here we analyze XRT and BAT data together with a common model. This is just a power law with an exponential cutoff. Why not 2 power laws? Simply because here we don't have enough signal to measure the high energy power law, so we put a cutoff. In red, you see XRT spectral data. In green, BAT. And what you see in blue and purple are Fermi data. Okay, for this gamma ray burst, there were also Fermi observations, so we added them and fitted everything together. This curvature here is not intrinsic, it's metal absorption, okay? So the model, the intrinsic model, is just a power law and with an exponential cutoff. And as you can see, the fit is very bad. Look at the residual. So there are some systematic behavior of the residuals. So we realized that the fit could be improved by adding
a break here. So we try to model with this kind of spectrum that now below the peak energy, there are two power laws and a break here. And the fit now is much better. The improvement is larger than 8 sigma. So here we have two characteristic frequency, the peak energy and this break energy that we discover thanks to the inclusion of XRT data. This is the absorbed spectrum, just for you to appreciate the intrinsic shape of the model that we are using to model the data. So two power laws connected here at, in this case, around 7 keV by a spectral break. So what is a spectral break? Let's go back to the comparison between observations and theory. Do we expect another break in synchrotron spectra? Well, yes, we were expecting it at much lower frequencies, but actually we can try to interpret this break as the cooling frequency. So this frequency marks the Lorentz factor of those electrons that cool on a dynamical time scale. Okay, so apparently, if we want to try to make this interpretation, particles, electrons are cooling very efficiently, but not at the high rate as we were expecting. Okay. But before claiming that this break is the cooling frequency, we need to make sure that the expectations for the photon indices is correct. It's, the observations are consistent with these predictions. So here the prediction is minus 0.5, as we already saw, and below the cooling frequency is minus 2/3. Okay. So these are the distributions of these two photon indices from observations. Before we call the photon index alpha. Now we have a break with two power laws, so we call them alpha 1 and alpha 2. And you see that they have large distributions. There are also errors in the estimates of these spectral indices, but the peak of the distribution is exactly where we have the predictions from synchrotron theory, so minus 1.5 and minus almost 0.7, okay? So this is very encouraging. And these breaks at low energies that were never found before have been later on found also in GBM data. So of course, the next step was to try to see if also other instruments detected this break. So we said, okay, let's assume that this break can reach quite large energies. Maybe also the GBM can detect them. So we selected the 10 most fluent gamma ray bursts in the GBM catalog and found those breaks also here. Okay, so here the break, for example, is at almost 200 keV, so it's well within the energy range of sensitivity of the GBM. So they were discovered in soft X-rays and thanks to XRT, but in the brightest gamma ray burst, they move to higher energy and can be found also in the GBM. And here you see the comparison with the expected slopes predicted by the synchrotron theory. Here again, some comparison between distributions of the spectral indices and expectations from the synchrotron theory. Okay, then a step forward. So if XRT is observing the gamma ray burst, then also UVOT is pointing to the gamma ray burst. So there are cases where we have also optical UV data during the prompt emission of the gamma ray burst. And from the light curve, you see that this emission is consistent with the prompt emission, shows a similar variability pattern. So we can associate this optical radiation with the prompt emission from the gamma ray burst. So we selected these cases and studied what these observations can add to this scenario. And here you see a spectrum now from UV to X13 to BAP. So we put everything together. This time in this paper, we used a synchrotron model. So the model is not just a broken power law with a cutoff or something, but we tested a real synchrotron model. And as you can see, the observation agrees very well with the theory. Okay. Okay, so last slide, sorry. I just want to show this discovery, thanks to XRT, how it has been used to deepen our understanding of the physics of gamma ray bursts. So we know that we don't understand much about prompt emission, but thanks to the identification of the cooling frequency, we believe that what we see is the cooling frequency, we can start constraining all these physical quantities that usually we cannot study. So you have a shell here at some distance r from the central engine. In order to describe the resulting radiative emission, you need these parameters: the bulk Lorentz factor, the number of electrons that are emitting, their Lorentz factor, the shape of the electron spectrum, and the magnetic field strength. Okay? If you know all this quantity, then you can predict the emission and compare with observations. Or actually, what we want to do is to start from observations and constrain all these physical quantities. So the observables are the variability timescale, the peak frequency of μm, called in this case the minimum, the frequency of the electrons with the minimum injection Lorentz factor, the peak flux that gives us the normalization of the spectrum, beta is the spectral slope above the peak, and now we are adding also the knowledge of the cooling frequency. So we are adding one more observable. What we obtained is as a function of the bulk Lorentz factor, so we cannot constrain all the quantities. There is some degeneracy left, so we presented the result as a function of the bulk Lorentz factor. We can estimate the magnetic field, the energy of the accelerated electrons, and the radius at which the emission was produced. So you see here that the magnetic field that we inferred from these observations is quite small. It's around 20, 30 Gauss. We were expecting a much larger magnetic field at these distances in the jet of gamma ray burst, like 10 to the 4, 10 to the 5. So we need some orders of magnitude. The energy of the electrons must be very large in order to explain observations. In the standard theory, it's around a few hundred. Instead, here we need to invoke very large Lorentz factor. So we need to invoke an acceleration mechanism able to accelerate particles at very large Lorentz factor. And then we found quite large radii of the region where the prompt emission is produced. Are we happy with these results? Not really, because these parameters are a bit unusual. Okay. So on one side, I think that study the spectrum at the lowest energy adding XRT data allows to reveal that the spectrum is consistent with synchrotron radiation. First result. Has a break, the spectrum and the spectral breaks never identified before, that is consistent with being the cooling frequency. But if we interpret, so if we believe to this interpretation and believe that this spectral break found in soft X-ray is the cooling frequency, then we end up with physical parameters of the emitting region that are very different from what was assumed before these discoveries, and these are a bit difficult to explain. So either we need to believe to the synchrotron interpretation, but change a bit our understanding, our description of what happens within the jet during the production from the emission, or maybe we need a different interpretation for this spectral break, okay? In any case, this is the most important progress, I would say, in the characterization from the emission spectra over the last 20 years. And I think that was a very nice example of how the study of archival data in a different energy range than the one usually used from the emission study has revealed something very new with important with an important impact on the physics of the jet of gamma ray burst. Okay, I will stop here. Thank you.
Yes. Yeah. So I didn't really understand the cooling. Like, it's at the same terms you have two kinds of electrons, like cooled and uncooled.
So no, it was before. They are all cold because they are still very energetic. Sorry, they are all hot because they are still very energetic.
Yeah.
But yes, so you have an evolving population of electrons because on one side we have a mechanism that keeps injecting new accelerated electrons, okay, freshly accelerated electrons. But then those electrons that you accelerated before start to cool down.
And this is the same magnetic field for those.
In the most basic scenario, yes.
So this is the one zone, two zone?
Yes, one zone.
This is one zone.
This is one zone. If you start to play with the magnetic field, then you can...
And you can have a strong magnetic field that accelerates them, and then a weak one where they
Exactly.
can reach higher energy.
Yes, yes.
This will be the two zone.
Yes.
I have another one.
Check also online.
Something.
So the one and microphone.
Please, Martin, go ahead.
Thank
you. Thank you very much, Lara. I have two stupid questions. Probably are trivial, but I'm just not sure. So, first question: when you were showing the prompt phase that like shifts into the afterglow, that blue prompt into red afterglow. Why is it always connected so smoothly? Why it's like matching each other more or less? Like if they are like two different processes, technically, like you had that they can be flares, but after all, like I think was maybe the slide before or after. Maybe I stopped you.
ACME le curve indici e window timing. i 4 pannelli delle curve XRT.
Allora questo.
Exactly this one, yeah, thanks. So why is it like this? Is just this cannot be just by chance, no? That it's like where the blue stops, more or less the red starts. So if they're like two completely different like processes with different spectra, why is it like that?
No, I'm not sure I understand the question. So in my interpretation, no.
Go ahead.
No, let me see if I can reply. So the point is that, yes, we have two phases from the afterglow, but they are not distinct in time. So they overlap. So when one is fading, but the afterglow is already working, so of course you have the composition of the two. So the sum of the two is always smooth, unless you have that the front ends and after a gap of time, you have the afterglow, then you have they are not connected. But in this case, they overlap in time. So what you see is always the sum of the two components that is as a smooth evolution. But maybe there was a different interpretation.
In addition to this, that is, of course, I have nothing to comment on it. I think that the specific question of Marco is here on the colors, but the colors here has nothing to do with the models or phases. It is just a color code for the different observing modes of XRT. And so
okay.
the blue is the so-called, sorry, I speak because I close to the mic. Is the so-called wind of timing, and that in the first part of the curve is always typically blue because it's when the afterglow is brighter, and if the count rate is higher than roughly 1 count per second, automatically XRT goes into the wind of timing mode. That has a higher timing resolution and a lot of stuff that our colleagues are going to tell you better tomorrow. Then after a while, the afterglow fades, the count rate decreases, and automatically XRT switches to the so-called photon counting. So and the two colors are so that the user knows in which mode the data are taken, and so they can handle it better. So it's not a model dependent stuff.
I'm sorry, I misunderstood the question. Yeah,
So the
blue and red is not prompt enough.
In the end,
okay.
yes, because it's the earlier part, and so it's more, let's say, prompt contaminated related.
Yeah, but here, for example.
Okay, so I understand now. So
yes,
the color, yeah, okay. Sorry. So the color is the like photo registering mode, like the brightness set to the brightness or to the flux. Okay. And the second question, if I can have like that gamma mean, that minimal injection energy, like why there is such a thing? Like is it determined by this Fermi second term, like a part acceleration mechanism that the acceleration process is not efficient below that gamma mean? That's why is it there? Because later you have even like a less energetic electrons that cool down already. So this gamma mean comes from the microphysics of the shock, or
Yes, so of course this is a simplified model. You will have a tail here, also here, but this is the typical energy to which you accelerate particles, and then you have the tail because this is a non-thermal process. Okay, so you don't have a temperature; it's not thermal. And of course, in a more realistic case, you have electrons populating also this part here, but you don't see them in the radiative part because in any case here you're dominated by the slope of the single electron spectrum. Okay.
Okay, so you see them only at the end when there is more of them, more of these electrons like below the gamma mean.
Yes, you are definitely
okay, where's the higher abundance of them? Okay, okay. Thank you so
at the
much.
end you are dominated by the cooled electron.
Okay, thank you.
Yes, my question might be stupid. How do you know the end of the prompt?
How do you know the end of the prompt? Variability is what distinguishes prompt from afterglow emission. But
stable. So when it becomes stable,
yes, but the separation is not so sharp. I mean, it's very difficult to say when the prompt stops and the afterglow starts, for example, here.
like you could have at the same time internal shocks in the jet and
Yes,
with
of course.
the
Yes, because you have many shells. So maybe the one emitted at earliest time are already interacted with the external medium, but you still have prompt emission from later shells. So yes, the two overlaps.
And then how do you get the T90?
Oh, the T90 is just a technical definition. So I think you you will have the count light curve and just you subtract the background. So you already have a defined window where you have a significant counts from the source. And then you take from 5 to 95% of the total count. So the initial times is when you start to accumulate at least 5% up to 95.
With the afterglow phase, like until the signal becomes less than the background. Like the entire light curve, you just subtract the background.
So the T90 is defined with BAT or GBM instruments where you have no afterglow. Okay. Yes.
So this does mean if you have, say, Fermi and BAT, they can have different T90s.
Yes.
Because it's different sensitivities and different energy band and things, but it's just you don't take the XRT into account, as Lara said. It's just the gamma ray instruments. Something else could be defined with the afterglow stuff and things, but T90 is an old definition from the days when you just had gamma rays and nothing else.
Okay, so the sensitivity short and long is.
Of course.
Because of
No,
X or something.
Yes, it was fancy that it was
Okay,
defined.
but another reference might have been other.
I mean, you do see a dip between round about 2 seconds with whichever instrument, whichever gamma ray instrument you look at. But we now know that there are short and long bursts are not that clear cut. Because if you think of them as it used to be short bursts were mergers and long bursts were collapsars and things, and not always that anymore.
No. In any case, the two distributions overlap.
That's why, but I thought that I didn't know it was instrument.
It's very difficult to define anything, right? When you get different instruments, things will look different.
Yes.
Can I have one more very short question?
Yes, I mean, we are already in discussion, so.
Yes,
Okay.
if you agree, we can consider that now we are in the open discussions. Yes. Please, Martin, go ahead.
Okay, yeah. There's something that I wanted to try to search for a long time ago, but I never done. Is there any like imprint of the prompt emission in the afterglow? Or is it like completely like washed out what happened during the prompt phase? Like we have many flares in the prompt, and can you see any signature of that in the afterglow, or anything's happening in the prompt? Does it have any impact of what's happening in the afterglow, or it's completely like washed out by the different deceleration, the interstellar medium mechanism, etc.? Since like it's a different process, or is there any memory of in the afterglow what happened during the prompt?
So if you're thinking at two shells that produce, let's imagine the internal shock model. So two shells that produce the prompt emission, and then the same merged shell that produce the afterglow. Is this what you have in mind? And you are asking if they two are connected in some way?
Well, maybe, or if there are three shells, whatever.
Maybe I'm overinterpreting, Martin. Maybe you are asking something like, if I just have the prompt emission, may I do some prediction of how the afterglow will look like?
Well, probably assuming, assuming the fixed external medium, like, yeah.
Giancarlo has another interpretation.
I know the question.
Please try.
Martin, what's the question? Probably we didn't understand it.
Because
Can you formulate? Can you expand a bit more your question to be clear?
No, like you have a prompt emission, and which, okay, maybe there are the internal shocks or something, and eventually it's I don't imagine like it's a smooth thing. So there are like some hydromagneto something dynamic flow of things of different velocities. When they merge, it still evolves somehow. So it creates a shock. The shock propagates, and eventually, like at later time, it starts to decelerate, but the engine can be still on somehow. So you can have an impact of other incoming shells, or is any activity from the prompt can affect how the emission in the afterglow. Like, does it? Can you say anything about the correlation between the prompt and the afterglow? Is there any like a correlation between these two, or it's completely independent always?
Okay, so
I would not say it's independent, but maybe I'm wrong.
So you mean the opposite of what I was saying? You are in mind prompt and afterglow from different shells, and you are asking if they impact each other?
Yeah, kind of. Or like imagine you have only one shell, so you have no prompt, and this would be stupid, right? So like if you have at least two shells, that creates a prompt emission, the gamma rays, and then if the entire like shock wave goes through the interstellar medium with the energy like accumulated over. But if you have new arriving shells or new energy injection, so you would have some impact from what was happening in the prompt in the afterglow, like maybe like a more activity in the prompt for a long duration prompt emission that would affect the afterglow or something like that.
Yes, sometimes we see bumps in the afterglow, so instead of being
are they correlated with the prompt emission, or is it just?
There are interpretations according to which this is energy injection from later shells emitted from the central engine that reach the shell that is producing the afterglow and inject some energy into the shell.
But the transport of this energy is dynamically transported to the afterglow and injected into the black hole. So these are late shells which inject energy in the afterglow, making it rise and appear brighter for a short while. I don't know instead if you were thinking about the possibility that you have the afterglow going, at some point the prompt emission starts again, so those photons from the medium transverse the region where the afterglow is producing photons. So you might have photon-photon interaction in the region where the afterglow is produced. In principle, you might have this, but on the other side, I guess the densities are so small that actually there is no detectable signature. From a theoretical point of view, it's something you can compute, but probably not.
Yeah, I was expecting something like that, but I was just, yeah, thank you.
Is there someone else on the note?
And I can see the question in
The chat.
the chart.
We still have 5 minutes or more if you want.
I
Yes.
might jump in about this topic. There is also a possibility also going back to the prompt and afterglow discussion. One can have also in the same time at late times where afterglow is emitting, you might have there are interpretations that say they might have some prompt related emission that you see in the time of the afterglow emission, which usually resembles a flare. And there are interpretations that this flare might be the emission coming from prompt at high latitude, which is more smooth in time and appears at lower energies, so in the X-rays rather than in gamma rays. This is also a running interpretation for some prompt-related emission, but during a time where you are dominated actually by the afterglow and the blast wave deceleration.
They coincide, they are separated in space.
Also the emission
coincide in time, probably
So-
they do not
Interact with each other.
They do not interact.
We just
They do
observe
not
them.
influence each other. It's just that you, the photons from these two different emission sites arrive to you at the same time.
It's only on a phenomenological point of view you observe them together.
There was another question down there.
Can you switch the page showing the different power law model? That page.
Which one?
The 3 different power law models.
The spectrum.
Equation of it. Yeah, this one. Let's see the strength of the magnetic field in the colored points. And later you mentioned we measured the strength of the magnetic field and it's much lower than expected. So we derive the strength of this magnetic field by measuring the cutoff points in the observed spectrum. Is it something or I missed something in between?
No, it's exactly this, the reason. So that's why I put this equation, because from here you see why if we measure a cooling frequency higher than expected, so in the X-ray range, it means that the Lorentz factor of the electrons emitting at these synchrotron frequencies is higher than we expected. So a large gamma C can be justified, can be recovered if you invoke a small magnetic field, exactly for this reason here.
I have a more generic question. So we see more long GRBs than short GRBs, okay? But is that the number of GRBs we're seeing, is that consistent with the results we're expected? So with the population studies and several evolution, are they consistent?
Yes, but I leave this question to Giancarlo. This is for you.
I must say that the ratio that we see is instrumental dependent. Different instruments, also those that Lara and Paolo mentioned, measure slightly different ratios. If I'm not mistaken, probably 1 to 4 in Batse, probably 1 to 3, or even less with the Swift. But if you, let's say, if you compare these ratios with the expected reconstructed population local rate of long and short GRBs respectively, which for long gamma reversed, so the local rate is the rate of a third of GRB jets oriented in every direction, so accounting for the fact that what we see is just a fraction of the population, because we see them as long gamma reversed when they don't kill us. But even on the end, you have hundreds of events present also. So if you construct the intrinsic population, you reach numbers which are of the order of 50 let's say, roughly long gamma reverse progenitors having a passive filter. And if you scale this number for the detection capabilities of this event, you match more or less the detection rates. The same goes for short-long bursts. There is a bit of tension, I would say, at the moment, with the fact that since for long gamma reverse, this is also consistent with the fact that since the progenitors are massive stars, that race that evolve quickly massive, and so we have a knowledge of the cosmic star formation rate, especially with low redshift, we extrapolate the local rate of long gamma reverse. We have also a good match, knowing the fraction of stars in the high mass distribution that produce long gamma reverse, and also is consistent with modular rescaling factor, which is related to the metallicity of the projection. So you have to rescale, integrate the mass function as something for the fact that the projectors should also be low or poor metal stars. When we go to short gamma reverse, there is a bit of tension in the fact that based on short gamma reverse detection, you have a rate, I don't remember exactly, but probably is around 1 of the capacity, which is in tension with the rate of binary neutron stars that were inferred in the initial run of the gravitational wave interferometer runs. That is now decreasing because, as Paolo said, there is no detection. And since these rates, the rate of progenitors and the rate of short GRBs are related by scaling factors, meaning that not all neutron stars might produce a successful jet and see the short gamma reverse. There is a scaling factor. This scaling factor is a bit evolving. So if at the beginning we were assuming that all neutron star mergers might produce a successful jet, we are now probably around the fraction, which is not 50% to 67. But it depends quite a lot on the normalization. The local rate of neutron star that we take into account, which from G gravitational wave observations now in 04 is reduced as a central values, but still affected by a large uncertainty in which so that's my feeling.
Thank you.
If there were not enough Newton star detection in all four, but the rate of short GRB stays the same, should it be like Newton stars produce more jets? The percentage of the Newton jets increases?
Well, there are different ways to accommodate this on a theoretical point of view. First of all, I mentioned just in the channel, there is a possibility there is an expectation that also neutron stars black hole may contribute, even though at a much lower. Because the reason is that despite the progenitors are probably more numerous than neutron star, the probability of having a successful jet and have the point of star depends a lot on the black hole, because if the black hole is too massive and too low spin, it eats the neutron star without the starting, so you don't do but there is also another point which is related to what Paolo mentioned, also used in the previous question, opinion, that is the fact that when we talk about rates of short GRBs, we are typically used to make calculation by calculating the distribution, the duration between 90 and 2 seconds, and taking everything which is less than 2 seconds. Why? From the already distribution that Paolo showed, from a couple of events which we could call imposters, that are long, apparently short gamma reverse to the long progenitor and vice versa, there is it could also help to reconcile this. So probably we are not in the situation where we need to invoke another channel completely unexpected to justify the rates in this case. So, one more question.
You always talk about non-thermal emission today, right?
Yes.
But is there also some thermal emission, and is it detectable in case, or is just?
Okay, I think I don't have backup slides to show that. So, thermal emission is expected because you expect some thermal component where the fireball, the jet, becomes transparent. So you expect that you have some residual energy that is released, photons can escape, and those photons are thermalized. So there are ways to predict and imagine a thermal component contributing to the prompt emission. And this is from theoretical expectation. From the point of view of observations, since the synchrotron emission has serious issues, I tried to convince you today that maybe we solved them, but for many, many years, there was a strong inconsistency with synchrotron radiation. Then people tried different models. For example, the convolution of thermal spectra that produce in total a non-thermal spectrum, or contribution of thermal components. So these are models where you try to explain the prompt emission as emission from two different components, thermal and non-thermal. And let's see if I have a plot. I must say, for sake of honesty, that also these breaks here have been interpreted as the signature for the presence of two components, because imagine that here, maybe it's easier here, you have one non-thermal component that has just one power law, like this. And then you miss this part here, then you add a black body, for example, and the combination of the two components results in this overall spectral shape, okay? So the presence of thermal components is still debated. Maybe you can see it here. So here we model with one single power law below the peak. And what you see from the residuals is it seems that there is some excess. So someone tried to recover this excess by introducing a second component, very narrow, because you need just to add some signal here. So a black body is the most natural candidate, okay? And this kind of modeling works. So you can actually fix the problem here with the residuals by adding a thermal component. Still, you have the problem that you need to explain the non-thermal component. In this paper here, we show that if you explain this break with the presence of a non-thermal component producing this bump, if you see it as a excess of radiation, then the non-thermal component, if you extrapolate it to the optical, will be here, will predict a very large flux. So the inclusion of prompt optical observations showed instead that the model is consistent really with the break and the hardening here of the spectrum. If you have non-thermal plus thermal, predictions are here both. Okay?
Thank you.
Okay, thank you. I think, okay, so we close the discussion here, and then thanks to Paolo and Lara for the presentation.
Okay, so thanks, Giancarlo. So today's session is over. Right outside of the main door here, there is a welcome cocktail for everybody. So enjoy. And tomorrow we will convene in this same room at 9. And
Did you say that tomorrow?
yes, tomorrow the other entrance, or you enter the movie.
Don't get lost.
So just outside here, the cocktail is already open. And thanks to people who attended remotely. See you tomorrow morning.